Have you ever looked up at the night sky and felt a profound sense of solitude? A feeling that we are adrift in an endless, silent ocean. It's a natural human emotion, but it's born from a trick of perspective. Our sky is not empty. It is crowded with wonders so immense and stories so ancient they defy our imagination. We see only the faintest echoes of their light, but they are their giants of fire and ice, cities of 1 trillion stars, and voids of unimaginable emptiness. What if we could pull back the curtain of night and see the universe for what it truly is? Tonight, we embark on that very journey. We will leave our familiar world behind to witness the celestial marvels that dwarf our own existence. We'll begin with a jewel of our own solar system, the majestic Saturn, and drift through its impossibly thin, shimmering rings. We will then leap across light years to a world known as Super Saturn, a gas giant adorned with a ring system so colossal it could swallow the orbits of our inner planets whole. From there, we will approach the ticking time bomb of the cosmos, the volatile red giant Betelgeuse, a star on the verge of a cataclysmic supernova. We will then stand in the shadow of Stephenson to 218, one of the largest stars ever discovered, a behemoth that would consume Saturn itself if placed in our sun's stead. We'll visit a rare and dying carbon star, a cosmic ember shedding its very essence into the void. Our voyage will then take us beyond the confines of our own galaxy to the glittering spiral of Andromeda, our closest galactic neighbor, a sprawling metropolis of stars with mysteries lurking in its core. And finally, we will venture into one of the greatest known structures in the universe, a supervoid, a region of such profound emptiness it challenges our very understanding of cosmic creation. Prepare yourself, for the universe is about to reveal its secrets. Our first destination is a familiar beacon in our night sky, but we are about to see it as never before. Saturn. It is not the planet itself that first captures the eye, but the breathtaking structure that encircles it, a celestial halo of impossible grace. These are not solid bands, but a phantom-like disk composed of trillions of icy shards, each a tiny moonlet dancing in a silent cosmic ballet. This magnificent structure tells a story of violence and creation, a story that began around 100 million years ago in that distant past. A large moon, a world of ice and rock, orbited Saturn. It moved with the steady, predictable grace of all celestial bodies, unaware of the immense power of its parent. But its orbit decayed. It drew closer, crossing a deadly threshold where the gravitational pull of the gas giant became an inescapable tidal force. The moon was pulled and stretched, the stress fracturing its icy crust until, in a final, catastrophic moment, it was torn apart. It shattered into a cloud of trillions upon trillions of glittering fragments. These remnants, the ghost of a lost world, could not escape Saturn's grasp. Governed by the unyielding laws of physics, they gradually spread out, forming a primary ring that embraced the planet. This initial ring was 1,000 times more massive than the one we see today, a truly monumental structure born from destruction. Over millions of years, this grand disk has been slowly diminishing. A portion of the debris was pulled into Saturn's swirling atmosphere, swallowed without a trace. Other fragments, like cosmic shrapnel, rained down upon Saturn's other moons, scarring their surfaces. and some were flung out of the system entirely, cast into the void of space. What remains is a delicate, dynamic, and ever-changing masterpiece, a constant reminder of the creative power of destruction. Even after centuries of observation, this structure continues to guard its secrets. The visible part of the rings stretches an astounding 280,000 kilometers from edge to edge. Yet they are, in most places, astonishingly thin, perhaps only 5 to 10 meters thick. Beyond these bright, visible rings lie even fainter structures, tendrils of dust and rarefied gas that extend outwards for millions of kilometers. Invisible from Earth, looking closer, we see that the rings are not a single, solid sheet. Through a telescope, the system resolves into a complex series of larger rings, each designated with a letter. And within these, we see a breathtaking complexity, thousands of slender, delicate ringlets, separated by narrow gaps. These gaps are carved out by the gravitational influence of Saturn itself and its shepherd moons, which patrol the rings like cosmic guardians, maintaining order in the beautiful chaos. Some gaps are vast, hundreds of kilometers wide, while others are mere whispers of empty space. The brightest and most magnificent of these is the Beering. It is a dense, brilliant band of ice and dust. But its outer edge holds a truly bizarre feature, a vertical rim that towers 2.5 kilometers high. A great wall of ice rising from the flat plane of the rings. It is a feature that defies easy explanation, a testament to the complex gravitational dynamics at play. As we drift through the ethereal earring, a faint, tenuous halo of microscopic ice crystals, we encounter its source, a small moon named with a diameter of only 500 kilometers. It is far from the largest of Saturn's moons, but it may be the most profound, for Enceladus is alive, not with biological life, as far as we know, but with geologic activity. This tiny moon is one of the few places in our solar system that exhibits cryovolcanism. From great fissures in its icy crust, powerful geysers erupt, spewing plumes of water vapor and ice particles into space. It is these plumes that constantly replenish the earring, feeding it with the very substance of the moon. But what does this mean? It means that beneath its frozen 75 Kelvin surface, something remarkable is hidden. Analysis of these emissions has confirmed our most incredible theories. A vast, global ocean of liquid water lies beneath the ice. Mathematical models suggest this ocean is kept liquid not by heat from the sun, but by the tidal forces of Saturn, which need the moon's core and generate warmth. The high concentration of salts and ammonia in this ocean acts as a natural antifreeze, allowing it to remain liquid even at temperatures below zero. Covered by a thermally insulating ice shell 2 kilometers thick, this hidden ocean is a tantalizing prospect. For within these geyser emissions, we have detected more than just water. We have found complex organic molecules, the very building blocks of life. Could it be that in the dark, pressurized depths of Enceladus's subsurface ocean, the conditions are right for life to begin? The question hangs in the cold silence of space, waiting for an answer. Moving further from Saturn, we encounter its largest satellite, a world shrouded in mystery, Titan, at over 5,000 kilometers in diameter. It is larger than the planet Mercury and is the second largest moon in our solar system. But its size is not what makes it so unique. Titan is the only moon known to possess a dense atmosphere. In fact, its atmosphere is 1.5 times denser than Earth's. Unlike our own oxygen-rich air, Titan's atmosphere is composed of over 98% nitrogen, with the rest being methane and other hydrocarbons. This dense, nitrogen-rich air, combined with the frigid surface temperature of -180 degrees Celsius, creates a world that is hauntingly familiar, yet profoundly alien. Solar winds, acting on the upper layers of its atmosphere, create a thick, orange, impenetrable smog, cloaking the surface from view in the optical range. Beneath this smog lies a landscape shaped by processes we would recognize, but with substances we would not. Here, at temperatures so low that water ice is as hard as rock, mountains are carved from frozen H2O, and in the lowlands and chasms, it is not water that flows, but liquid ethane and methane. Great lakes and rivers of hydrocarbons dot the surface, making Titan the only other world in our solar system with stable bodies of liquid on its surface. Titan is a world of incredible potential. While its internal processes constantly replenish its atmosphere, it is in a slow battle against Saturn's magnetic field and the solar wind, which strip away its gases. But this process will take billions of years, far into the future, when our sun expands into a red giant. It will vaporize the hydrocarbon haze and melt the eternal ices of Titan. For a fleeting moment in cosmic time, this moon could become a temperate, water-rich world, a far more favorable place for the genesis of life. The story of Titan, it seems, is only just beginning. Our journey now takes a great leap, 434 light-years from Earth, to a star system that redefines our concept of rings. Here orbits an object informally known as Super Saturn. It is a young world, only 15 to 16 million years old, and is either a massive gas giant 20 times the mass of Jupiter or a brown dwarf, a failed star. But what makes this object truly staggering is the system of rings that encircles it. If Saturn's rings are a delicate halo, Super Saturn's are a cosmic hurricane. The transit method has revealed a system of at least 37 distinct rings, but their scale is almost incomprehensible. The outer radius of the largest ring extends to 6 astronomical units. To put that in perspective, that is a distance comparable to the orbit of Venus and is 640 times the radius of Saturn's entire main ring system. This circumplanetary disk is so massive that its total mass is greater than that of the Earth itself. Mathematical models tell us that such colossal structures are not stable and will gradually disintegrate over hundreds of millions of years. But within this instability, there is evidence of creation. A large gap in the ring system, about 4 astronomical units out, points to the existence of an exomoon in the process of forming a world about 80% the mass of Earth, powerful enough to clear its own orbit of debris. One can only imagine the view from the surface of such a world. In its sky, the brown dwarf would appear 70 times larger than our full moon, its soft glow turning the deepest night into a perpetual, misty twilight. Instead of stars, the sky would be crisscrossed by the vast, luminous bands of the rings, stretching from horizon to horizon. It would be a sight of enchanting, terrifying beauty, a world born within a celestial structure so grand it challenges the very limits of what we thought possible. We now turn our attention to one of the most famous stars in our night sky, a beacon of ominous red in the constellation of Orion. This is Betelgeuse, a red supergiant in the final turbulent throes of its existence. It is a star living on borrowed time, and in late 2019, it gave astronomers a scare. Its luminosity suddenly and dramatically plummeted to just 36% of its standard brightness, an event known as the Great Dimming. For a few months, the scientific community buzzed with the possibility that we were about to witness a supernova, an explosion so bright it would rival the moon in our sky. The panic subsided as Betelgeuse returned to its normal brightness in April 2020. The cause of the dimming was later confirmed to be a giant cloud of gas and dust ejected by the star itself, which temporarily obscured its light from our view. But the event served as a stark reminder. Betelgeuse could go supernova at any moment. It might be tomorrow, or it might be 100,000 years from now. We simply do not know. So what is this cosmic behemoth? Betelgeuse is a star of immense proportions, with a mass around 17 times that of our Sun. Its radius, however, is a staggering 700 to 880 times larger. If we were to place Betelgeuse in the center of our solar system, it would swallow Mercury, Venus, Earth, and Mars, with its outer layers. Stretching out into the asteroid belt, the star has no well-defined edge. Its outer layers are incredibly rarefied, bleeding off into a vast gas nebula formed by eons of stellar wind and massive ejections of its own substance. Its luminosity is just as extreme, fluctuating between 90,000 and 150,000 times that of the Sun. Yet for all this power, its surface temperature is relatively cool, giving it its characteristic red hue. The processes driving this star are unstable and chaotic. The outer layers pulsate unpredictably, causing its brightness to vary on multiple cycles. This is the fate of all massive stars. Having exhausted the hydrogen in their cores, they begin fusing heavier elements. This process causes them to swell to incredible sizes, becoming red giants or supergiants. But this is a short-lived phase of glory. The life of a star is determined almost entirely by its mass. Small stars, like red dwarfs, will burn for trillions of years. Sun-like stars will end their lives by shedding their outer layers to form a planetary nebula, leaving behind a white dwarf core. But for massive stars like Betelgeuse, the end is far more spectacular. Once the star's core has fused elements all the way up to iron, the process stops. Iron fusion consumes energy rather than releasing it. At this point, the outward pressure from fusion that has supported the star for millions of years ceases. Gravity wins. In a matter of seconds, the core collapses catastrophically, shrinking from the size of the Earth to a dense ball just a few kilometers across. This incredible compression heats the core to billions of degrees and triggers a flood of neutrinos. The collapse then rebounds. The core violently expands, sending a titanic shockwave hurtling through the star's outer layers. This is the supernova. The explosion is so powerful that it forges elements heavier than iron gold. Lead, uranium, and blasts them across the galaxy. These elements will one day seed new clouds of gas and dust, forming new stars and planets. When Betelgeuse finally explodes, what will be left behind? Given its mass, it will likely leave behind a neutron star, an object so dense that a single teaspoon of its material would weigh billions of tons. Or, if its true mass is on the higher end of estimates, it could collapse into a black hole. Thankfully, at a distance of 500 to 650 light-years, we are safe from the direct effects of its blast. The gamma-ray burst will be too diffuse to harm us, and the ejected material will take 6 million years to reach our solar system, where it will be repelled by our sun's solar wind. All we will witness is the magnificent light show a new, brilliant star in our sky that will shine as brightly as the full moon 4 weeks before gradually fading away. A final, beautiful farewell from a dying giant. For a long time, the star Uy-Scuti held the title of the largest known star. But in 2020, data confirmed a new champion, a star so mind-bogglingly enormous it forces us to reconsider the limits of stellar size. Its name is Stephenson 218, located nearly 20,000 light-years away, hidden behind giant clouds of cosmic dust. This red supergiant is a true colossus. Its estimated radius is an almost unbelievable 2,150 times that of our Sun. This means its volume is roughly 10 billion times greater. If Stephenson 2-18 were placed at the center of our solar system, it would not just swallow the inner planets. It would extend beyond the orbit of Jupiter and engulf Saturn and all of its glorious rings. It would take a beam of light nearly 8.5 hours to travel across its equator, the same amount of time it takes sunlight to reach the distant dwarf planet Pluto. Despite its immense size, its surface temperature is relatively low, about 3,200 Kelvin, which is why it shines with a deep red light. This also means that most of its energy is radiated in the invisible infrared spectrum. It is so vast and diffuse that its average density is incredibly low, comparable to the Earth's atmosphere at the very edge of space. It's a miracle of physics that an object so tenuous can sustain the nuclear fusion that makes it a star. Like Betelgeuse, Stephenson 2-18 is in the final stage of its life. It is a veritable star, its luminosity and size likely fluctuating unpredictably. It too will end its life in a spectacular supernova, seeding the galaxy with heavy elements. Seeing this star, even just through data, is a humbling experience. It reminds us that the universe is constantly building on scales that are truly astronomical, creating objects of such magnificence that they almost seem to be a product of fantasy. But Stephenson 2-18 is real, a silent, burning giant in the distant darkness. Because of its vast distance, we are seeing it as it was 20,000 years ago. For all we know, it may have already exploded, its light from that final cataclysmic event already hurtling towards us through space, a postcard from the past that has yet to arrive. Our next stop brings us to a different kind of dying giant, a rare celestial object known as a carbon star. 650 light-years from Earth lies CW Leonis, a red giant in its final life stage. But its story is one of a unique chemical transformation. In its youth, it was a star several times more massive than our Sun. As it aged and exhausted its hydrogen, it began to fuse helium in its core. This process, known as the helium flash, dramatically transformed the star, causing it to swell and its outer layers to cool. But the crucial event in its evolution was the creation of carbon. In the star's interior, helium nuclei fused to form vast quantities of carbon, which were then dredged up to the surface by powerful convection currents. Now, the atmosphere of CW Leonis is richer in carbon than in oxygen. This simple chemical imbalance has profound consequences. The star is enveloped in a thick, sooty nebula of carbon and oxygen gas. This is because the star is constantly shedding its mass, losing an amount equivalent to 7 Earths every year. This nebula, which has been growing for at least 69,000 years, is a treasure trove for astronomers. Within it, spectral analysis has revealed around 70 different chemical compounds, including carbon dioxide, water, and ammonia. But the biggest mystery was the water. How could a carbon-rich star, where all available oxygen should be locked up in carbon monoxide, produce scorching hot water vapor? The current hypothesis is as dramatic as it is fascinating. The star is unstable, and ruptures occasionally appear on its surface, creating low-density areas. Through these windows, powerful ultraviolet radiation from deeper within the star can escape. This radiation blasts apart molecules of silicon oxides and carbon, freeing oxygen atoms to react with hydrogen, forming water vapor. It's a complex and violent process that gives this dying star one of its most peculiar features. CW Leonis is a star in its autumn years. Within the next 10,000 to 30,000 years, it will exhaust its fuel. It will cast off its outer layers in a final explosive pulse, creating a beautiful planetary nebula. At its center will be left a white dwarf, an incredibly hot and dense stellar remnant that will slowly fade over trillions of years, eventually becoming a cold, invisible black dwarf. The carbon and other heavy elements it has created and scattered into space will one day become part of new stars and new planets. They may even become part of new life, a final, enduring legacy of a star that turned itself into a cosmic factory of creation. We now leave the confines of the Milky Way, venturing across the intergalactic void to our nearest major neighbor, the Andromeda Galaxy. 2.5 million light-years away, it appears in our telescopes as a faint, fuzzy patch of light. But, as we draw closer, its true form is revealed. A majestic spiral galaxy, a sprawling city of stars, even larger than our own, containing perhaps 1 trillion suns. At its heart lies a region of incredible energy and mystery. Like our galaxy, Andromeda has a supermassive black hole at its center, one that is 50 million times the mass of our Sun. But Andromeda's core is peculiar. It appears to have a double nucleus. One bright cluster of stars sits slightly off-center, while a dimmer, smaller concentration marks the true galactic core where the black hole resides. The leading theory is that this is the remnant of a smaller galaxy that Andromeda consumed in the distant past, its core now orbiting the larger galaxy's center before it is eventually swallowed completely. The central bulge of Andromeda is a dense sphere of older yellow stars, packed tightly together. From this bulge, great spiral arms coil outwards, regions of active star formation where interstellar dust and gas are compressed to create stellar nurseries. Here, brilliant young blue stars light up the nebulae, giving the arms their characteristic shimmering, colorful appearance. Within these arms, we find some of the most extreme stars in existence, like A Andromedae, a luminous blue variable. These are incredibly rare, massive, and unstable stars, their luminosity varying wildly as they teeter on the edge of self-destruction. AE Andromedae is 50 to 120 times the mass of our Sun and shines with the light of up to 700,000 suns. It will not live long. Within the next million years, it will detonate in a hypernova, a supernova of unimaginable power, leaving behind a black hole. Andromeda is a galaxy with a violent history. It is surrounded by the shredded remains of over 100 smaller galaxies that it has absorbed over billions of years. We can see these as great stellar streams, rivers of stars orbiting the main galaxy. One of its most significant collisions happened about 800 million years ago when a satellite galaxy, now known as M32, plunged directly through Andromeda's disk, punching a gigantic hole in one of its spiral arms. M32 survived, but it was stripped of most of its stars, leaving behind a compact, dense core. This cosmic dance of creation and destruction is far from over. Andromeda and the Milky Way are bound together by gravity, and we are hurtling towards each other at over 300 kilometers per second. In about 4.5 billion years, our two galaxies will collide and begin a long, slow process of merging, a cosmic dance that will last for hundreds of millions of years. The night sky of our distant descendants will be a spectacular, terrifying sight as the two galaxies tear each other apart and reassemble into a single, giant, elliptical galaxy. Our journey to Andromeda is not just a visit to a neighbor. It is a glimpse into our own distant, cataclysmic future. For our final destination, we travel to a place defined not by what is there, but by what is not. We journey into the great nothing. Our universe is structured like a cosmic web, with long filaments of galaxies and galaxy clusters surrounding vast, empty regions called voids. These voids make up about 50% of the volume of the observable universe, and they are the largest structures in existence. We are heading to one of the most immense voids ever discovered, the Canes Venatici, located 1.5 billion light-years from Earth. Its scale is difficult to comprehend. It is 1 billion light-years across. This single patch of empty space is so vast that it could contain 10,000 galaxies the size of the Milky Way. Yet within this mind-boggling volume, we have found only 17 small galaxy clusters huddled together in one small corner. What is it like inside such a void? It is the closest thing to a perfect vacuum that exists. The density of matter is less than 1/10 of the universal average. For every cubic centimeter of space, there is less than half a molecule of matter. The radiation from distant galaxies is negligible. All that remains is the faint, leftover glow from the Big Bang, the cosmic microwave background, and a sea of undetectable neutrinos. It is a place of profound silence and darkness. Imagine being on a planet within one of those few lonely galaxies. Inside the supervoid, the night sky would be almost completely black. The nearest major galaxy would be hundreds of millions of light-years away, an impossibly faint smudge, visible only to the most powerful telescopes. Would a civilization born in such emptiness ever be inspired to look up? Would they ever develop astronomy, ever learn that they were not alone in the universe? It is a question that highlights how fortunate we are to live in a relatively dense, star-filled neighborhood. Even more mysterious is the Eridanus supervoid, also known as the CMB, cold spot. It is 1.8 billion light-years across, and it is significantly colder than the surrounding universe. The standard model of cosmology cannot fully explain this anomaly. Some scientists have proposed exotic explanations, such as the influence of supermassive chunks of dark energy, or even the mind-bending possibility that this cold spot is a bruise left over from a collision between our universe and another. We have no definite answers. The great voids are not just empty spaces. They are profound mysteries, challenging our most fundamental understanding of the cosmos. Our journey into the Canes Venatici supervoid has shown us the profound emptiness that dominates the universe's volume. It is a silence and a darkness, so complete that it can feel like the end of the story. But it is not. These voids, as vast as they are only one half of the universe's grand design, for in between them, connecting everything, is their opposite, a structure of breathtaking complexity and scale, the cosmic web. If the voids are the great empty oceans of the cosmos, then the cosmic web is the network of continents and islands, where all of life, all of light, and all of matter resides. It is an intricate, three-dimensional lattice of unimaginable size, composed of colossal filaments of gas and dark matter, stretching for hundreds of millions of light-years. These filaments are the celestial highways of the universe, and along them, galaxies flow like rivers of light, drawn together by the inexorable pull of gravity. Where these filaments intersect, they form dense, brilliant notsta, great galaxy clusters, sprawling metropolises containing thousands of galaxies, each a star city in its own right. This structure was not built by chance. It is the ghost of the universe's earliest moments, an echo of tiny quantum fluctuations in the primordial soup of the Big Bang, magnified to an astronomical scale. In the very first instance of creation, some regions of space were infinitesimally denser than others. Over billions of years, gravity has worked on these initial seeds. The denser regions pulled in more and more matter, forming the filaments, while the less dense regions were left behind, expanding to become the great voids. But the matter, we can see the galaxies, the stars, the shimmering gases, only the decoration on this structure. The true architect of the cosmic web is invisible. It is a mysterious, unseen substance that we call dark matter. This ghostly scaffolding makes up nearly 85% of all matter in the universe. It does not shine, it does not reflect light, and it does not interact with us in any way we can directly perceive. We know it is there only through its gravitational influence, the way it herds galaxies into formation, the way it bends the light of distant objects, and the way it dictates the very structure of the cosmos. The filaments of the cosmic web are, in essence, vast rivers of dark matter, and the galaxies we see are merely the luminous foam on the surface of these invisible currents. To journey along one of these filaments would be Lictus, the universe. In all its glory, you would drift past an endless parade, great elliptical spheres of ancient gold and irregular clouds of chaotic starbirth. You would see them drawn together, slowly but surely, towards the great intersections, the cosmic crossroads, where the largest structures in the universe are born. It is at these intersections, in the very heart of the most massive galaxy clusters, that we find the most violent and energetic phenomena the universe has to offer. As we travel towards the heart of a distant galaxy cluster, a point of light begins to dominate our view. It is not a star, though it shines with the light of trillions of them. It is not a galaxy, though it outshines its entire host. This is a quasar, a quasi-stellar object, and it is one of the most luminous and enigmatic phenomena in the cosmos. When quasars were first discovered in the 1960s, they baffled astronomers. They appeared as star-like points of light, yet their spectra revealed they were moving away from us at incredible speeds, meaning they had to be located at immense cosmological distances. But if they were so far away, how could they possibly appear so bright? What kind of engine could generate such an astonishing amount of energy? The answer, when it was finally pieced together, was both terrifying and magnificent. A quasar is not an object, but an event. It is the brilliant death cry of matter as it is consumed by a supermassive black hole at the center of a young galaxy. In the early universe, galaxies were awash with gas and dust, the raw fuel for star formation. This material, drawn by the immense gravity of the central black hole, did not fall straight in. Instead, it formed a vast, swirling disk around the black hole, known as an accretion disk. As the material in this disk spirals inwards, it is accelerated to near the speed of light. The friction and compression within this disk are so intense that it heats up to millions of degrees, glowing with a ferocity that can be seen from across the observable universe. The quasar is the light from this superheated accretion disk. It is a beacon powered by gravity itself. The energy output of a quasar is almost beyond human comprehension. A typical quasar can release more energy in a single second than our sun will in its entire 10 billion year lifetime. They are so bright that they act as cosmic lighthouses, allowing us to probe the most distant reaches of space and time. Because of their immense distance, the light from quasars has been traveling for billions of years to reach us. When we observe a quasar, we are not seeing the universe as it is today. We are seeing it as it was in its infancy. We are looking back in time to an era when the universe was young, chaotic, and filled with these voracious engines of light. But a quasar's reign is fleeting. They are a feature of young galaxies, rich in fuel. As the supermassive black hole consumes the surrounding gas and dust, or as powerful jets of radiation launched from its poles blow the material away, its fuel source dwindles. The accretion disk thins out, the friction subsides, and the brilliant light of the quasar begins to fade. Over millions of years, it flickers and dies, leaving behind a quiescent, dormant, supermassive black hole at the center of a now mature galaxy. Our own Milky Way likely hosted a quasar in its distant past, and the slumbering giant at our galactic center, Sagittarius A, is the silent remnant of that brilliant, bygone era. Quasars are a reminder that the universe was once a far more violent and luminous place, and that at the heart of nearly every galaxy, including our own, lies the potential for a fire that can outshine 1 trillion stars. We have spoken of supermassive black holes as the engines of quasars and the anchors of galaxies. But what are these objects? What happens when gravity, the most relentless force in the universe, becomes so powerful that nothing, not even light, can escape its grasp? The answer lies at the end of a star's life, when a truly massive star, one more than 20 times the mass of our Sun, exhausts its nuclear fuel. It can no longer support itself against its own immense weight. The core collapses in on itself in an instant. If the core's mass is great enough, not even the incredible density of a neutron star can halt the collapse. The material is crushed down to a point of infinite density and zero volume of singularity. At this moment, a black hole is born. The singularity itself is hidden from the universe, shrouded by an invisible boundary known as the event horizon. This is not a physical surface, but a mathematical one. It is the point of no return. Anything that crosses the event horizon, a planet, a star, a beam of light, is trapped forever, its fate sealed within the black hole's depths. The gravity at the event horizon is so extreme that the escape velocity exceeds the speed of light, the ultimate speed limit of the cosmos. Black holes warp the very fabric of spacetime around them. Imagine spacetime as a flat, stretched rubber sheet. A star or planet would create a small dip in this sheet. A black hole, however, creates a bottomless well. Light from distant stars that passes near a black hole will follow this curvature, its path bent as if by a giant lens. This phenomenon, known as gravitational lensing, is one of the key ways we can detect black holes, as they distort the images of the galaxies and stars behind them. Time itself is a victim of a black hole's gravity. According to Einstein's theory of general relativity, the stronger the gravitational field, the slower time passes. For an observer watching from a safe distance, an object falling towards a black hole would appear to slow down as it approached the event horizon, its light becoming redder and dimmer. It would seem to take an infinite amount of time to actually cross the boundary, frozen forever at the edge of the abyss. For the object itself, however, time would pass normally, and it would cross the event horizon in a finite amount of time, on a one-way journey to the singularity. For decades, we believed that nothing could ever escape a black hole. But in the 1970s, Stephen Hawking proposed a revolutionary idea. Due to quantum effects near the event horizon, black holes are not entirely black. They should emit a faint, steady stream of particles, a phenomenon now known as Hawking radiation. This process causes the black hole to lose mass, ever so slowly, over unimaginable timescales, trillions upon trillions of years. Far longer than the current age of the universe. A black hole will evaporate completely, vanishing in a final flash of gamma rays from the stellar mass. Black holes left behind by dead stars, to the intermediate mass black holes thought to lurk in the hearts of globular clusters, to the supermassive giants that command the centers of galaxies. These objects are a fundamental component of the cosmic ecosystem. They are not just cosmic vacuum cleaners. They are agents of creation and destruction, shaping the evolution of galaxies, powering the brightest objects in the universe, and challenging our most fundamental understanding of space, time, and gravity itself. When a massive star dies, its fate is not always to become a black hole. If the collapsing core is not quite massive enough to form a singularity, the collapse is halted by one of the most powerful forces in nature, neutron degeneracy, pressure. The inward crush of gravity is so immense that it overcomes the electrical repulsion between particles. Electrons are forced to combine with protons, creating a sea of neutrons packed together as tightly as physically possible. The result is a neutron star, an object that represents one of the most extreme states of matter in the universe. A neutron star is, in essence, a giant atomic nucleus. It packs the mass of 1.5 suns into a sphere only about 20 kilometers. In diameter the size of a city, the density is beyond comprehension. A single sugar cube-sized piece of neutron star material would weigh as much as Mount Everest. Its gravity is equally extreme. If you were to drop an object from just 1 meter above its surface, it would accelerate to over 7 million kilometers per hour before impact. But their density is only part of their incredible nature. As the star's core collapses, its rotation speed increases dramatically due to the conservation of angular momentum, the same principle that causes a spinning ice skater to speed up when they pull their arms in. A star that once took weeks to rotate can be spun up to hundreds of rotations per second. This rapid rotation, combined with the star's incredibly powerful magnetic field, trillion times stronger than Earth's, turns the neutron star into a cosmic lighthouse. As the neutron star spins, it emits powerful beams of radiation from its magnetic poles. If these beams happen to sweep across our line of sight, we observe a regular pulse of energy. We call such an object a pulsar. For a time, the regularity of these signals led some to believe they might be beacons from an alien civilization, earning them the nickname LGM-1 for little green men. We now know them to be the natural, breathtaking consequence of stellar death in some cases. The magnetic field of a neutron star is even more extreme. A magnetar is a type of neutron star with a magnetic field 1,000 times stronger than that of a typical pulsar, the most powerful magnetic field known in the universe. This field is so intense that it can buckle the star's crust, causing starquakes. These events release colossal bursts of energy in the form of X-rays and gamma rays. In 2004, a flare from a magnetar located 50,000 light-years away was so powerful that it measurably compressed the Earth's ionosphere. Neutron stars are the universe's ultimate physics laboratories. They are crucibles where matter is subjected to conditions of pressure, density, and magnetism that we can never hope to replicate on Earth. They are the crystalline corpses of once mighty stars, spinning in the darkness, flashing their rhythmic pulses across the cosmos as a perpetual monument. Our journey has taken us through a universe of brilliant light of stars, nebulae, and galaxies. But everything we have seen, everything that has ever been observed by any telescope in human history, amounts to less than 5% of what is actually out there. The rest of the universe is composed of two enigmatic substances that we can neither see nor comprehend: dark matter and dark energy. Together, they are the stagehands of the cosmos, the invisible forces that dictate its structure, its evolution, and its ultimate fate. First, there is dark matter. We have already encountered it as the invisible scaffolding of the cosmic web. But how do we know it's there? The first clues came from observing the rotation of galaxies. The stars at the outer edges of spiral galaxies were orbiting far too quickly. According to the laws of gravity, based on the visible matter alone, These stars should have been flung off into intergalactic space. The only way they could be held in their orbits was if the galaxy contained a vast, invisible halo of extra mass exerting a powerful gravitational pull. This unseen mass is dark matter. We see its effects everywhere. We see it in the way galaxy clusters hold together, preventing their members from flying apart. We see it in the way its gravity bends the light from distant objects, a phenomenon of gravitational lensing that allows us to map its distribution even though we cannot see it. Dark matter is the silent majority of the universe's matter, the gravitational glue that holds the cosmos together. What is it? We simply do not know. It is not just ordinary matter that is too dim to see. It has to be something entirely new, a particle not included in our standard model of particle physics. The leading candidates are called WIMPs, or weakly interacting massive particles, hypothetical particles that interact with normal matter only through gravity and the weak nuclear force. Scientists in deep underground laboratories around the world are engaged in a modern-day treasure hunt, using incredibly sensitive detectors to try and catch a fleeting glimpse of a WIMP as it passes through the Earth. The discovery of the dark matter particle would revolutionize our understanding of physics. If dark matter is the force that pulls the universe together, dark energy is the force that is pushing it apart. For most of the 20th century, astronomers assumed that the expansion of the universe, which began with the Big Bang, must be slowing down due to the mutual gravitational attraction of all the matter within it. But in the late 1990s, observations of distant supernova revealed something astonishing, something that no one expected. The expansion of the universe is not slowing down, it is accelerating. Some unknown force is counteracting gravity on the largest scales, pushing galaxies away from each other at an ever-increasing rate. This mysterious, repulsive force is what we call dark energy. It appears to be a property of space itself, a kind of intrinsic energy of the vacuum. As the universe expands and more space is created, more of this energy comes into existence, driving the acceleration. It makes up nearly 70% of the total energy density of the universe, making it the dominant component of the cosmos. Like dark matter, we do not know what dark energy is. It could be the cosmological constant, an idea Albert Einstein once proposed and then abandoned, calling it his biggest blunder. It now seems he may have been right all along. Or it could be something even more exotic, a dynamic field that changes over time. Unraveling the mystery of dark energy is perhaps the single greatest challenge in cosmology today, because the answer will determine the ultimate destiny of our universe. The discovery of dark energy has placed a profound question before us. How will the story of the universe end? With this mysterious, repulsive force now in the driver's seat, the fate of the cosmos seems to be headed in a specific and rather lonely direction. This most likely scenario is known as the heat death or the Big Freeze. In this future, the accelerating expansion driven by dark energy will continue forever. Galaxies will be pushed further and further apart. In about 100 billion years, all galaxies outside our own local group will have receded beyond our cosmic horizon, their light no longer able to reach us. The night sky will become a dark, empty void with only the stars of our own merged galaxy. The Milkomada galaxy remaining visible, the story does not end there. Over trillions of years, the fuel for star formation will be exhausted. The last stars will be born, live their lives, and die, leaving behind a graveyard of stellar remnants. White dwarfs, neutron stars, and black holes. The universe will become a place of perpetual twilight, lit only by the faint glow of these dying embers. Even these will eventually succumb to the passage of eons. White dwarfs will cool to become black dwarfs. Neutron stars will radiate away their energy. And through Hawking radiation, even the black holes themselves will evaporate over unimaginable timescales, until nothing is left but a dilute, featureless soup of photons and fundamental particles, cooled to a temperature infinitesimally close to absolute zero. The universe will become a cold, dark, and empty place, devoid of structure, life, or meaning. This is the big freeze, a slow, quiet fading into eternal night. While this is the most widely accepted scenario, other, more violent possibilities exist, depending on the true nature of dark energy. If dark energy is not a constant, but a force that grows stronger over time, a hypothetical substance known as phantom energy, then the universe could be heading for a big rip. In this scenario, the repulsive force of dark energy would eventually become so strong that it would overcome all other forces. First, it would tear apart galaxy clusters. Then, it would overcome the gravity holding galaxies together. In the final moments, it would be strong enough to overcome the electromagnetic and nuclear forces. Solar systems would be unbound, planets and stars would disintegrate, and finally, atoms themselves would be ripped apart. The very fabric of spacetime would be torn asunder in a final, cataclysmic end. There is a third, now less likely possibility. That was once the leading theory, the Big Crunch. If there were no dark energy, or if its effects were to someday reverse, the gravity of all the matter in the universe could eventually halt the expansion and pull everything back together. The universe would begin to contract, galaxies rushing towards each other in a reversal of the Big Bang. The universe would grow hotter and denser, ending in a final fiery singularity, perhaps setting the stage for a new Big Bang in a cyclical process of death and rebirth. Our current evidence points strongly towards the cold, quiet end of the Big Freeze. But the universe is full of surprises. The discovery of dark matter and dark energy has shown us that our understanding is far from complete. The ultimate fate of the cosmos remains one of the greatest unanswered questions, a final chapter in the cosmic story that is still being written. We have journeyed from the familiar shores of our own solar system to the dawn of time and the predicted end of the universe. We have stood in the shadow of cosmic giants, witnessed the fury of dying stars, and peered into the heart of galactic monsters. We have navigated the luminous highways of the cosmic web and contemplated the profound emptiness of the great voids. We have grappled with the invisible forces of dark matter and dark energy, the ghostly puppet masters that command the cosmic stage. What this grand tour reveals, more than anything, is that our universe is far stranger, far larger, and far more magnificent than we could ever have conceived. And yet, for all its alien grandeur, it is our home. The carbon in our cells, the iron in our blood, the calcium in our bones, all were forged in the crucible of a star that lived and died billions of years ago. We are not separate from the universe, we are a part of it. We are the means by which the cosmos has, for a brief moment, on a tiny world, become aware of itself. The questions that remain are as vast as the cosmos itself. What is dark matter? What is dark energy? Are we alone in the universe? What happened before the Big Bang? We do not have the answers. But the quest to find them is perhaps the noblest of all human endeavors. It is a quest driven by our most fundamental trait, our insatiable curiosity. As long as we continue to look up, to wonder, to explore, and to question, the journey will never end. The universe is waiting, full of secrets yet to be discovered, and our exploration of the infinite cosmos has only just begun.